Hello and welcome to Blockchain 101. And now that you have an understanding of the basics of cryptography, it is a good time to talk about blockchain because it is a great application of cryptography. So this lecture is a 10,000 feet view of blockchain. The goal is to get you familiar with the history and motivation behind blockchain, its core concepts, and the types. To understand blockchain, let's start with some history. You have probably heard of Bitcoin. So Bitcoin was started by Satoshi Nakamoto in 2008. So it is a digital cryptocurrency which works on peer-to-peer networks. So it is decentralized, meaning that there is no central bank that operates this digital currency. So how does Bitcoin work? Well, the technology behind Bitcoin is blockchain. And so if you have been using the term Bitcoin and blockchain interchangeably, now is the right time to correct it. In simple words, blockchain uses peer-to-peer topology to securely store and transfer digital assets without requiring any intermediaries. So you can use it anywhere you need to achieve decentralization and store or transfer digital assets securely. This digital asset could be money, medical record, vote, or anything else. So basically it can be used anywhere where we have these requirements. For example, healthcare, education, government, manufacturing, distribution, etc. So blockchain is a linear chain of blocks, as the name suggests, meaning it grows in one direction. And once a block is added, although it can be read, it cannot be modified. Each block has a specific number of transactions. These transactions could be anything. For example, it could be a transfer of money, it could be a creation of a new patient health record, etc. Each block also has a header which contains various attributes such as timestamp, hash value of the block, hash value of the previous block, etc. Since blockchain is based on peer-to-peer technology, you must be thinking, well, how do we achieve security and trust in a decentralized environment? For example, how do you ensure nobody tampers with the data and modifies it? And when someone sends you, let's say, 5 bitcoins, how can you be sure that you have them or that the sender does not deny having sent them? Also, who maintains the database since there is no central authority? Well, the security in blockchain is achieved using cryptography. Two most important concepts are hash functions and digital signatures. Hash functions are used to achieve integrity and ensure that once you save data on blockchain, no one can change it. And so if someone changes the data on blockchain, you can also easily detect it through the hash values. In other words, blockchain provides immutability. Therefore, it is ideal for applications where you need to maintain history of who performed a certain action and also ensure that nobody tampered with this data. Digital signatures are used in blockchain to authenticate the sender of a transaction and also to achieve non-repudiation, so that someone cannot deny having performed a certain transaction. Let's briefly look at hash functions. So hash functions turn any length input into a fixed size output, which is the hash value, or also known as a message digest. Two different input values have different hash values, assuming the algorithm does not cause collisions, or very few collisions. Any change in the input value will change the output value. And they are one-way functions, so given a hash value, it is hard to get back to the input value. There are various hashing algorithms out there, for example, MD5, secure hashing algorithm, which has a 256-bit version and a 512-bit version, and also Kechik. The one used in Bitcoin blockchain is SHA-256, whereas Kechik 256 is used in Ethereum blockchain. Okay, so hash values are great, and we can store data in a block and also its hash value. But what if someone changes the data in a block and also its hash value? Can we detect that? Because none of the other blocks, for example, in this case, block number 1 and block number 3 are not going to be affected if we change data in block number 2. So the answer is no. That's why we don't really store hashes and data like this in a block. What we do instead is something like this. While calculating the hash of the current block's transactions, we also use the previous block's hash value. Now, if I change something in block number 2 here, I will have to change the hashes of all subsequent blocks from block number 2 and onwards. Otherwise, this discrepancy will be easily detected. This is because hash value of block number 3 is dependent on hash value of block number 2, which just got changed. Hash value of block number 4 is dependent on hash value of block number 3. So we also store previous block's hash values inside the current block to help us detect changes. All blocks except the first block, known as the genesis block, contains hash of the previous block. If you have ever created a Bitcoin wallet, you have probably seen a Bitcoin address like this. This is basically what identifies you and is what you give others so that they can send you Bitcoins. It is basically your public key. So when you create the wallet, a public and private key pair is generated. Now, whenever you need to do a transaction, you sign it using your private key, and then the receiver verifies the signature using your public key, which is your Bitcoin address, and which is part of the transaction. So no one can modify this transaction because then the signature will also change. And no one can create a signature for you because nobody else has your private key. And no one can deny having sent the transaction because there is a signature which only they could have created. You can also authenticate the sender by verifying that the public key that they're giving you really belongs to them if you're able to verify their digital signature. As we know that blockchain uses a distributed ledger or a distributed database. So every node participating in this peer-to-peer network has a copy of the database. So how do we ensure that at a given moment in time, all of these nodes who have their own copies of the blockchain have the correct data on blockchain, since there is no central database? Well, we achieve trust in blockchain using consensus protocols. The consensus algorithms ensure that all nodes are able to come to a consensus on one state of the blockchain, and they all have the same copy of the ledger. These algorithms also determine who will add the new block to the blockchain after it has been validated. That's because if multiple nodes try to add a block, there will be problems such as redundancy and inconsistency. Now, there are various consensus algorithms that are being used and developed. There is proof of work, which is the oldest and most widely used in Bitcoin and Ethereum blockchain. And this one is based on computing power of a node. But there are other algorithms which do not require computing power. These include proof of stake, proof of elapsed time, proof of deposit, and proof of capacity. Let's look at proof of work. In this consensus protocol, each participating node tries to solve a mathematical puzzle first to be able to add the new block to the blockchain. An example of a puzzle is to compute a hash value for the new block that follows a certain format, such as it begins with a certain set of zeros. This is hard to do and requires a lot of computing power. you have to try different nonces or random numbers, which when added to the block's content will generate a hash value in the required format. If not, you keep trying until you are able to satisfy the criteria. And if you're able to satisfy the criteria, then this means that you have solved the puzzle, and if you were the first one, you will be able to add the block to the blockchain, you will get a reward, and you will broadcast that new block to all nodes. And so the idea is that if you are spending a lot of processing power, it is highly likely that you are not a malicious node. And so after every 2000 blocks or so, or in about 2 weeks, the protocol looks back at the last 2000 blocks and measures how long it took to solve the puzzle. And if the time taken is very small, then the difficulty is adjusted accordingly so that only a few nodes are able to solve the puzzle. So this is basically what we also call mining. You might already be familiar with this term. If a miner solves the puzzle, they are given a reward, which is 12.5 bitcoins currently on Bitcoin blockchain and 3 ethers on Ethereum blockchain. And the rewards don't stay constant. They are halved every few years or after a certain number of blocks have been mined, as you can see here on the right. In 2009, the miner's reward was 50 bitcoins, whereas now it's only 12.5 bitcoins, and it's soon going to be reduced further to 6.25 bitcoins. So what are blockchain nodes? The nodes form the infrastructure of a blockchain. A node can be a computer, a laptop, or a mobile phone. These are all nodes. There are two types of nodes in blockchain, full nodes or partial nodes, which are also known as light nodes. Full node is any computer that has a copy of the entire blockchain. So it needs a large amount of storage capacity. For example, as of 1st May 2020, the size of Bitcoin blockchain is 275 gigabytes. Full nodes do the work of verifying the blocks that are getting added to the blockchain. And full nodes can also optionally serve as miners by running the mining software, assuming they have a huge computing power, in addition to a large storage capacity. On the other hand, the partial or light nodes are basically users of blockchain. For example, a mobile phone that is accessing the Bitcoin blockchain through the Bitcoin wallet app is basically a light node. So what are the different types of blockchain? Well, there are two basic types of blockchain, a public blockchain or a private blockchain. A public blockchain, as the name suggests, is open to all and the data on the blockchain is publicly accessible. Also, anyone can take part in the blockchain by being a node. A classic example of a public blockchain is Bitcoin's blockchain, as we will see in a bit. A private blockchain, also known as a permissioned blockchain, is specifically created for a single organization, such as a hospital. So who accesses the blockchain is basically controlled. Even the number of nodes in the blockchain is pre-specified. A group of organizations, for example 3 hospitals, can also create a blockchain together, which will then become a federated blockchain. But it's still a private blockchain and it's still a permissioned blockchain. Now, to create these private blockchains, we can use various open source platforms. Ethereum and Hyperledger are 2 open source platforms created for developing private blockchains and decentralized applications that make use of these private blockchains. So they consist of frameworks and tools that you can use to build your own blockchain and develop decentralized applications. As we know that in Bitcoin blockchain, we are performing simple conditional transfer of Bitcoin values from one account to another. There is no complex logic there. What if you want to develop a decentralized application that uses blockchain, but that has a complex logic to store and retrieve transactions from the blockchain? This is where smart contracts come into the picture. So smart contracts can be thought of as a piece of code that creates a mechanism to interact with the blockchain and store and retrieve information from it. So kind of it sits in the middle between the blockchain and the front end of your application. Let's say you are developing a web application that is basically a decentralized application, and you're also creating a private blockchain that you want to store information to and retrieve information from. Now all that logic that will be used to determine when to create a transaction, who creates the transaction, what kind of transaction is to be created, all that is going to be stored in the smart contract. So smart contract is basically a set of functions that are called by the front-end application to access blockchain. The Ethereum Foundation introduced a framework for smart contract code execution in 2013. And so these smart contracts are deployed on all nodes in a blockchain network. Now that we have looked at the main concepts on blockchain, let's look at the operations that occur in a blockchain to store new data. So as soon as there are new transactions, they are broadcasted to all nodes in the network and are validated by each node on different criteria such as size, fees, syntax, digital signatures, etc. All these new transactions that pass the validation checks are then gathered into a pool of unconfirmed transactions. A set of these unconfirmed transactions form a block. To add this block to the blockchain, miners compete by solving a puzzle. Each miner could have picked a different set of unconfirmed transactions, which is completely okay because the solved block is broadcasted to all nodes and verified by other nodes by recalculating its hash, and a consensus on the next block is achieved. The transactions in this new block are removed from the list of unconfirmed transactions. This new block is then added to the blockchain, and the transactions in the block are confirmed. Typically, one block has around 2,700 transactions in the Bitcoin blockchain and approximately 100 transactions in the Ethereum blockchain. To reinforce all these concepts, let's look at Bitcoin's blockchain. Again, this is a public blockchain, so anyone can access and see all the data. So you can see over here, we have the latest unconfirmed transactions. Basically, these are all valid transactions that were validated by all the nodes in the blockchain network, but these are still not part of the blockchain, meaning that they are not added to any new block on the blockchain. Right, so you can click on any one, you can see information about it. And so we know how much amount was in the transaction, right? Both in Bitcoins and also in dollars, right? So these are unconfirmed transactions. Now, you can also take a look at the blocks, the existing blocks which have a set of transactions which have been added. These are confirmed transactions which have been added on the blockchain. There's also information on difficulty. As we discussed, the difficulty is adjusted every few weeks. So you can see that over time, the difficulty has been increased. So let's take a look at the blocks. So you can see over here, we have the topmost block. We have its hash value. We also see information about the mining, how long ago this was mined. And we have information about the miner as well, right? So you can see information about this specific block by clicking on it. And so we have various information, what time this block was created, its hash value. There is the difficulty information here. We also have information about the number of transactions, approximately 2,000, and so on. And so you can also see there's a block reward. Basically, this is the reward that was given to the miner. That's 12.5 bitcoins. Also see this nonce information. What is this? This is basically the number only used once, that number that the miner added to the transactions in this block to be able to create the hash value, which has a certain format. So as you can see over here, the hash value has this specific format, right? It has a specific number of zeros in the beginning. To be able to get a hash value of that format, you have to do some kind of brute forcing. You have to try different random numbers, add them to the data, and see if the resulting hash value actually satisfies the criteria. And then you can also see all these transactions that are part of this block. The from and to address, and so on. And the signatures. So that brings me to the end of this lecture. Thank you, and I hope the 10,000 feet overview of blockchain was useful. If you are interested in learning more, I suggest looking at the Hyperledger platform's Fabric project. It has a very easy to follow tutorial on the necessary installations and how to create a basic smart contract and deploying it on the nodes in a test network.